Nice to meet you, everyone. Today, I am talking about the Kepler's second law for the introduction to astronomy. Before going to our main topic today, let me talk something about the introduction to astronomy. So first, what does astronomy aim? That is, indeed, complete knowledge on all the celestial objects and phenomena. Those include mechanics of suns, planets, and comets, structure and evolution of stars, nebulas, galaxies, etc., and extreme events, including supernova, gamma-ray burst, pulsar, black holes, and also the origin and history of the universe. Of course, to clarify all these targets is not easily done, but let's keep challenging. Then we may know 1. Where this universe goes, and 2. Why this universe exists in some day in future. Okay, so now we know the motivation for astronomy. The next question is how to approach and investigate these targets. There are indeed two main categories of astronomy. The first one is observational astronomy, and the second is theoretical astronomy. In the observational astronomy, that is to observe the celestial events and collect their data. Those include infrared astronomy, ultraviolet astronomy, optical astronomy, and recently you may know that gravitational wave can be also a powerful proof for observational astronomy. On the other side, in the theoretical astronomy, the purpose is to build the model to explain the observed events. Those include stellar dynamics, stellar evolution, large-scale structure, and black hole, and blah blah blah. From the interaction between this observational astronomy and theoretical astronomy, we aim to get the new knowledge on the new event. So this is a typical process of evolutions in astronomy. First, accurate and sufficient data become available thanks to the observational astronomy. Second, from those data, theoretical astronomy provides a new and sophisticated theory. By that theory, a novel inspiration rises for the further observations. Then we return to one to repeat this evolutional process. So, in the remaining part of this lecture, I'll show you a typical example of this process that was done by Brahe, Kepler, and Newton. Let me introduce these three big names in astronomy. The first one is Tycho Brahe, who was a Danish astronomist. His astronomical observations were an essential contribution to the scientific revolution. Accuracy of his data has been the best in human eye observations until today. Kepler had great respect for Tycho's methods and the accuracy of his observations. Then, after Tycho Brahe, there was the second one, Johannes Kepler, who was a German astronomist. By utilizing the legacy data done by Tycho Brahe, Kepler established three laws. The first law is that the planetary orbit is not a circle, but an ellipse. The second law says that surface velocity of planet's orbit is constant. Then, the third law tells that the square of planet's orbital period is proportional to the cube of the semi-major axis of its orbit. Please note that these three laws are still empirical before the Newton, who is the third last big name here. Then after Johannes Kepler, we got Isaac Newton, who was an English astronomist. As well known, he is the pioneer of classical mechanics, but not only for that, but also of the physics today. In his book Philosophiae Naturalis Principia Mathematicae, the fundamental laws of mechanics are presented, which is symbolized by this equation. What Newton did, indeed, by using formulas in his textbook, all the Kepler's laws can be derived. That means Newton established a simple and beautiful theory for astronomy. The works by Brahe, Kepler, and Newton is a typical example of the evolutions in astronomy. Then, of course, after these three people, further observational and theoretical astronomies were promoted. Alright, so in the remaining part of this lecture today, I'll show you how we derived the Kepler's second law by solving the two-body problem in Newton's mechanics. Okay, let's recall what was the second law by Kepler. That was surface velocity of planet's orbit is constant. And this figure and formula represents this law symbolically. So our main task today is to derive this result by solving the two-body problem in Newton mechanics. So in the step 0 assumptions, we consider two objects with masses m1 and m2, and their potential and force are given as this, namely the force is obtained from the gradient of the potential v, and the equation of motion is given as this equation 1. And also for the potential, we assume that the central force or the central potential, which depends only on the distance between two objects, but not on the angular variables. In step 1, first we determine the relative coordinate, that is r1 minus r2. Thus, the original equation of motion 1 is transformed as this, and here we have changed the variables of the gradient from r1 or r2 to the common variable r. Then, by calculating something, finally, we can transform this equation 1 into the final form here, that is, mu r double prime is minus gradient of potential v, that is nothing but force F. And here, mu is the so-called relative mass. Step 2, angular momentum. Okay, from this transformed equation of motion 2, now let us consider the angular momentum of the relative motion. That is, the capital L is r cross p. And we consider the time evolution of this vector L. Then, by calculating something, the first term should be always 0, because the cross term of two vectors in parallel should be 0. Then, for the second remaining term, this is also 0 because we assumed the central force. So the vector F is always in parallel to the coordinate r. Then we have indeed proven that the time evolution of this angular momentum is always 0, that is, the conservation of angular momentum. Now the remaining problem is really small, because we already showed that the angular momentum is constant. Then the surface velocity is represented as, here vector sigma is indeed proportional to angular momentum L. Therefore, if angular momentum is constant against the time evolution, the surface velocity is also. And this is nothing but the Kepler's second law, which was our first target. So congratulations, we did our task today. After session, we have shown that the Kepler's second law can be obtained by solving the two-body problem in Newton mechanics. Indeed, the first and third laws by Kepler can be also proven by solving the same problem. But for that purpose, one additional assumption is necessary. That is, the potential is proportional to the 1 over r. This is nothing but the gravitational law. So finally, let me close this lecture by sending you some message. To become a good astronomer, you need to be trained for not only for the classical mechanics, but also for the electromagnetic theory, thermodynamics, quantum mechanics, relativistic theory, computational physics also, and for many things indeed. The process is indeed a little bit hard, but let me encourage you to study for the future development in astronomy. Thank you very much for your participation today.